Good morning. I'll give a few more minutes for people to filter in. Let's get the dot cam set up. Okay. Looks like people are starting to filter in. I want to give a little bit more time for other folks to arrive. So I'll talk with you guys just a little bit about what it is we're going to do today. Today we're going to be learning partial fractions. We introduced this last time, and I think you guys saw a little bit more than my other class did. But I'm going to kind of start from scratch and pretend as though you guys haven't seen anything at all. In theory, I should be able to trust that everybody learned this in pre-calculus and just jump straight to the calculus bits, but I know that that's not the truth. So even if your pre-calc class did cover partial fractions, and they don't always, I think we would probably all benefit from the reminder. There are a few sort of definitions that we're going to need to get started. And while I'm letting people filter in here or we're waiting, I'll go ahead and write those down. Surely everybody here has worked with rational functions, but we may not remember the strict definition. So a rational function is one which can be expressed as a ratio of polynomials. So mathematicians love analogies. Polynomials are the function version of whole numbers. Right? One of the things mathematicians do is we study function spaces. So rather than thinking of like the real numbers as a space where you can study things that have to do with real numbers, you can talk about the space of all continuous functions or the space of all polynomial functions. The space of all polynomial functions in function land is kind of like the space of all integers in real number land. You can kind of think of polynomials as being the function versions of whole numbers. And so a rational function then is like the function version of a rational number, i.e. a number that can be written as a ratio of integers. Specifically, the thing to remember here is that the top and bottom have to be polynomials, right? So no square roots of x, no e to the x, no none of that stuff. Just positive integer powers of x. There's one other definition we need to get started here, and that's the definition of a proper rational function. So a proper rational function is a rational function so the top and bottom are both polynomials in which the degree of the numerator is strictly less than the degree of the denominator. Right? So since it is a rational function, the top and bottom are both polynomials, meaning each one has a degree. Remember, the degree of a polynomial is the largest power of x that shows up. A rational function is called proper if the degree of the top is strictly less, and the strictly here is important, not less than or equal to, strictly less than the degree of the denominator. So just to make sure we're comfy with these definitions, I'll give some examples. The function x over x minus 1 times x plus 1. This is a rational function. Because the top and bottom are both polynomials. And it is proper. Because the degree of the bottom is 2, and the degree of the top is 1. The function x cubed over x cubed plus 1. This is also rational. Because the top and bottom are both polynomials, but this one is not proper. We call those improper. Because the degree of the top and the degree of the bottom are the same. They're both degree 3. The degree of the top is not strictly less than the degree of the bottom. So if a rational function is not proper, we call it improper. And then finally, if you had something like this, this is not a rational function. So not every function that is a fraction is rational. This guy is not rational because the bottom is not a polynomial. The top is a polynomial of degree 0, but the bottom is not a polynomial. E to the 2x, e to the x, those are exponential functions. And remember, polynomials have to be positive integer powers of x. This is not a positive integer power of x at all. There is a substitution you could make to turn this into a rational function, but as it is, it's not rational. So any questions on these definitions or examples, the sort of classification scheme? So a rational function is a function that is a fraction of polynomials. And we call it proper if the degree of the bottom is strictly bigger than the degree of the top. If the degree of the top is strictly less than the degree of the bottom. Partial fractions partial fraction decomposition, which is what we're learning. I'm going to abbreviate it PFD, is an algebra trick to write a proper rational function as a sum of simpler rational functions. So partial fractions is not calculus. We use it to make certain calculus things easier, but PFD itself is just algebra. And you can only do it to proper rational functions. So this guy, I can't do any PFD to. This guy, I can't do any PFD to. But the guy at the top, he is ready for PFD. Before we get into how to do PFD, and you've seen an example last time, but before we get into it formally today, I want to talk to you about how you would deal with something like this. Could you show me using the React tool, just give a thumbs up React, if you've seen polynomial division in the past, how to long divide two polynomials. It's okay if you don't remember all the details. I'm just curious who's seen it and what sort of proportion of pre-calc teachers teach it. If you took pre-calc with me, I know you've seen it, but I don't think anybody here has taken pre-calc with me. Okay, so maybe just two of us, that's fine. If you look in your modules, you'll see here, under the review material, there's a few links to how to divide polynomials. All right, these bottom three are all about polynomial division. Also, if you dig around in Paul's online notes, the algebra review, I'm pretty sure he talks about it there too. Well, maybe not. Yeah, no, he's got multiplying polynomials, but nothing for division. So if you want more examples of polynomial long division, check out any of these three bottom videos. I'm going to do one of them today. It's not too hard. And essentially, that's how you would deal with this. So if you have an improper rational function, polynomial long division is a way to rewrite that as a polynomial plus a proper rational function. And it works just like long division worked in second grade when you were first learning how to long divide numbers. So this is a procedure to write an improper rational function as a polynomial plus a proper rational function. So if I hand you an improper rational function, then you need to polynomial long divide. That will give you a polynomial piece, which we call the quotient, and then also a proper rational function, which will come from the remainder. So remember when you first learned how to do long division, you want to divide 28 by 9. And you say, okay, well, 9 goes into 28 3 times, but then there's a remainder of 1. So 28 divided by 9 would be 27, 3 plus 1 over 9. So similar to that, if I wanted to divide x cubed by x cubed plus 1, and remember, this is what our first improper rational function looked like there. It was x cubed over x cubed plus 1. We start just by writing it out like this, just like you would in second grade. The polynomial upstairs goes here. The polynomial downstairs goes here, because I want to divide this by this. The trick is to pay attention only to the lead terms in each step. So I start by asking, what must I multiply this by in order to get this? And that's not too hard. What do I need to multiply x cubed by in order to get x cubed? That's 1. So that goes up here. Then you multiply this by this and you distribute everything. That's not hard in this case. 1 times x cubed is x cubed, plus 1 times 1 is 1. And then you subtract this row from the row above. It's sometimes helpful to remember that this is x cubed plus 0x squared plus 0. Plus 0x plus 0, I should say. So x cubed minus x cubed, that's 0. 0x squared minus 0x squared, 0x minus 0x. 0 minus 1 is minus 1. So when I subtract those two rows, this is what I get, just negative 1. And now the degree here is lower than the degree here. So there is no polynomial I can multiply x cubed by in order to get negative 1. So this is the end of the long division process. You're done. This piece is called the quotient. This piece is called the remainder. And what this tells me is that x cubed over x cubed plus 1 is equal to this quotient, 1, which is my polynomial, plus this remainder over this divisor. So if you did see this in pre-calc and they had those problems where you had to write this ratio as a quotient plus a remainder, this is why. Because if I wanted to integrate this, I could integrate this instead. This piece is very easy to integrate, and in general, the polynomial piece is always easy to handle. This piece is now a proper rational function. So right here, I promised you would get a polynomial plus a proper rational function. And if my original objective was to integrate this, I would then run partial fractions on this guy. So again, for more practice with polynomial long division, please take a look at the resources I've posted for you in the modules. There will be several problems in your homework that require you to do this, and there may be a problem on the test that requires you to do this. Okay.
Is this going to be on the homework that's due on Monday?
Let me see. So it is on your current homework, but I don't believe it's set to be due Monday. Let me take a look because we were thinking of having the exam. Oh, that's right. Yeah, we had to move the exam. Let me see. So right now, the current homework, homework 5, is set to be due next Friday.
Okay.
That's when we were originally going to have the test. Now remember, we're going to have to move the test to the following Monday. So I'll be moving this homework's due date to the 5th as well.
And the study guide opens today as well?
Yes, I'll be dropping the study guide today. Yep.
Okay.
All right. So let's get into the meat of partial fractions. The basic idea is this. I want to write a complicated rational function as a sum of simpler rational functions. So procedure to write a complicated proper rational function as a sum of simpler ones. And what you have to think about is the concept of a common denominator. You know that when you add up two rational functions and you have a common denominator, the denominator of the result has all the factors of the original rational functions multiplied together. So we want to undo having a common denominator.
What's after simpler?
Proper rational, simpler ones, sorry, ONES. So in general, what you're going to do here is you're going to factor the denominator of your function and then ask, how could that function have arisen as a sum of rational functions where each rational function in the sum has one of the factors of the thing you're trying to split up? It's easiest to start visualizing this by looking at examples. And let's look at the example that we had at the start. X over x minus 1 times x plus 1. How could I get something like this? By adding up two simple, proper rational functions. Well, if I added something whose denominator was x minus 1 to something whose denominator was x plus 1, then when you put those two together, they would have to have this denominator, right? And if they're each going to be proper rational functions, since the degree of the downstairs here is 1, the numerators would have to be constant. So something like this could have come from something like this plus something like this. That's it. That's the core idea behind PFD. And then we want to find the numbers A and B. The kind of large-scale picture here is beginning with something that looks like this. You have to ask, what sort of things like this could you have added up to get it? And as long as the factors of the denominator are nice and simple, then the setup will always look something like this, which is relatively simple. So we want to find A and B to make this true. Is the goal clear? The justification for this is a little bit complicated. To say for sure this had to have come from something like this is not entirely obvious. And if you're curious about where it comes from, I'd be happy to talk about it in office hours. It's coming from a field of math called linear algebra, where we talk about spanning sets and bases for vector spaces. But for us, I think intuitively it's relatively satisfying. You know, if you add two things like this, you'll get something with this denominator. So then we just try to solve for A and B. If I cross multiply both sides by x minus 1 times x plus 1, on the left-hand side, I'll just get x, right? X minus 1 times x plus 1 times this. Both of the factors cancel from the denominator. On the right-hand side, if I multiply this by x minus 1 times x plus 1, the x minus 1s will cancel, and I'll be left with a times x plus 1. And similarly here, if I multiply this by x minus 1 times x plus 1, the x plus 1s would cancel, and I'll be left with b times x minus 1. So after your PFD setup, that's the name of this line. This is called the PFD setup, where you
express your rational function as a sum of simpler ones without knowing those numbers, a and b. Once you have your PFD set up, you cross multiply to get rid of all the denominators. You kill the denominators. The next step is to multiply everything out on the right-hand side. So this is ax plus a plus bx minus b. And then you group like terms. You group powers of x. So this is ax plus bx. That's a plus b times x. And you group the constant terms. That's a minus b. Now I have a question to ask you. If I told you that 3x squared minus 2x plus 1 was equal to alpha x squared plus beta x plus gamma, could you tell me what alpha, beta, and gamma have to be? What is alpha?
3.
Yeah. And beta?
-2.
Good. And gamma would have to be 1, right? Well, very, very similar to that, what I have here is, let's look at that left-hand side. That's 1x plus 0 equals a plus bx plus a minus b. So 1 has to be equal to a plus b. And 0 has to be equal to a minus b. It's the exact same thing. Everybody see it? X is 1x plus 0. And this is a plus bx plus a minus b. So just like this tells me alpha has to be 3, this tells me a plus b has to be 1. And this tells me a minus b has to be 0. And the result is a 2x2 system of linear equations, which you can then solve for the numbers a and b. Once you have the numbers a and b, you have your partial fraction decomposition. How do you solve this linear system? There's more than one right answer here.
Could you use elimination?
Good answer. If you add these two, if you add row 1 to row 2, and here's the notation I like for this, my new row 2 is my old row 2 plus my old row 1. So this arrow says I'm transforming the system according to this rule. I use a capital R for the new row and little r's for the old rows. Row 1 isn't changing. I still have a plus b equals 1. But row 2, when I add this to this, I'll have 2a. When I add this to this, I'll have 0b. And when I add this to this, I'll have 1. So now equation 2 says that 2a equals 1, which means a's got to be 1/2. And if I take that and I plug it into equation 1, so subbing a equals 1/2 into equation 1, we find 1/2 plus b equals 1, which implies that b is also 1/2. So now you're done with the partial fractions. You found a and you found b such that my function is equal to a over x minus 1 plus b over x plus 1. Therefore, x over x minus 1 times x plus 1 is equal to 1/2 over x minus 1 plus 1/2 over x plus 1. And if I wanted to integrate this, I could integrate these instead. And that's why we talk about this in Calc 2. So the integral of x over x minus 1 times x plus 1 dx is equal to 1/2 integral 1 over x minus 1 dx plus 1/2 integral 1 over x plus 1 dx. They each require a little substitution. Here I'll let w be x minus 1. Here I'll let z be x plus 1. dw is dx. dz is also dx. And you get integral 1/2 integral 1 over w dw plus 1/2 integral 1 over z dz, which is 1/2 natural log w plus 1/2 natural log z plus a constant, which is 1/2 natural log x minus 1 plus 1/2 natural log x plus 1 plus c. So this is the game, and it's not terribly hard. Most of the work in these problems is going to go into solving the linear system. Once you arrive at this line, you get your linear system. The degree of the denominator here was 2, and we had to solve a 2 by 2 linear system, 2 equations, 2 variables. In general, if the degree of your denominator is n, you will have to solve an n by n linear system. And you may recall from your algebra classes that solving linear systems can get quite tricky as the size gets larger. So you may end up wanting to employ some matrix methods to solve the larger linear systems. I'll do my best to not hit you with horribly hard examples, because I don't find solving linear systems all that exciting, and I expect that you probably don't either. But there are a handful of important examples that we need to be ready to handle. Another thing I want to take a second to address is the setup. Here, the PFD setup was very simple. I had 2 distinct, meaning different, not repeated, linear factors in the denominator. So to get started on a problem like this, you need to factor the denominator. And your PFD setup is determined by the shape of the denominator. So because I just had this x minus 1 factor, I had this term in my PFD setup. because the denominator had this x plus 1 factor, I had this term in my PFD setup. The PFD setup is the all-important kind of jumping off point. If you get this setup wrong, then the problem is hopeless. If you don't know how to set up the PFD, then the problem is hopeless. So the next thing I want to do is give you guys kind of a PFD Bible, like the trig sub Bible, right? If you see this, then you do this. This was a relatively simple problem because this is a relatively simple denominator. But if this term was squared, like x plus 1 quantity squared, things would be a little bit different. Or if the denominator contained an irreducible quadratic factor, a quadratic that could not be factored into two linear terms, that would also complicate things. The good news is that every polynomial, and you again may or may not remember this from your algebra classes, every polynomial can be factored over the real numbers into linear factors and irreducible quadratic factors. There's no such thing as an irreducible cubic polynomial. There's no such thing as an irreducible quartic polynomial. They can always be factored into quadratics and linear factors. And if you're willing to work with complex numbers, they can always be factored into linear factors. But our focus in this class is on real numbers, so I won't take you there, but I will show you how to handle the two less pleasant cases. Any questions on this problem before I leave it? The places where people get lost or make mistakes, the wrong PFD setup, and right now you don't really know anything about where these come from besides what I've told you, so don't stress about that. But then also here, going from this to the linear system, do we see how you pass from here to here? It really is just this thing. But to get there, first you have to multiply all of this shit out and then collect together all the powers of x. I'll give you a second for anybody who's still writing stuff here. And then if there are any questions, please let me know. I would like to address them. So I'll do it like this. That's all the PFD work for this problem. Okay, good. I'm glad, Carl. Yeah, it's kind of very intuitive, right? That you just match up the coefficients of x on both sides. Startlingly powerful technique. The magic is that it's not an equation, really, it's an identity. You might remember the difference between an equation and an identity. An equation has like one or two or finitely many solutions for the number x. An identity is a statement that is true for every number x. Since this is meant to be an identity, this is an identity. And the only way for the polynomial on the left to be equal to the polynomial on the right is if their coefficients are identical. A plus b is the coefficient of x on the right. 1 is the coefficient of x on the left. So a plus b has to be equal to 1. A minus b is the constant term on the right. 0 is the constant term on the left. So a minus b has to be equal to 0. Since this is an identity, these must both be true. And this will always be a linear system. So you can fall back to your stuff on linear systems to find a and b from there. It's very cool shit. I'll never forget the moment this clicked. I was in MAC2312.002. I was struggling really hard, and my pre-calc teacher was a brutal savage. He beat the shit out of us every opportunity he had, metaphorically, of course. And I was sitting with this 45, 50-year-old math tutor who himself did not understand how to pass from here to here. And we just looked at it and stared at it. And there was just this moment where it clicked. So I want to give you guys a second to have that click moment. do we see where this system comes from? Here. Are there any questions about where any of these pieces came from? Good, yeah, Carl. So 1x plus 0. My left-hand side is just x. And I know that where I'm going is to compare coefficients. So think about your definition of a polynomial of degree n, right? Polynomial of degree 1 is some constant times x plus some other constant. So I want to write x in that standard polynomial form. X is 1x plus 0. This guy is this. I'm just writing it in this kind of absurd way to help me see what the coefficients are. The linear coefficient is 1 because x is 1x, and the constant coefficient is 0 because there isn't something here. If this was like 2x plus 5, then a plus b would be equal to 2, and a minus b would be equal to 5. Cool stuff, yeah? I'm a fan. All right, let me show you the partial fractions Bible, and then we'll look at a few more complex examples. Partial fractions, remember, I'll always abbreviate PFD. If you're religious, please don't be offended. I'm not claiming this to be scripture. I'm just saying it's the thing to which we refer. If the denominator contains, and then I'll list different sort of factors you could have here, then your PFD setup must contain, and I'll list the corresponding pieces for the PFD setup here. If your denominator contains something like x minus r, a simple linear factor, then your PFD setup will contain one term, and it will be a constant, which I'm writing as capital A, over that factor. If your denominator contains a repeated linear factor, like x minus r squared, or x cubed, or x plus 1 to the 5, in general, x minus r to the m for multiplicity. This is what's called a repeated linear factor. Then your PFD setup has to have all the things that could have contributed to that being in the denominator. Which means, yeah, you're going to have an a over x minus r, but also you could have b over x minus r squared, or c over x minus r cubed, all the way up to whatever over x minus r to the m. You have to build up. Because if you add all these guys together, the common denominator from all of these is just this. So having this factor in the denominator of your original function means it could have come from any combination of things like this. And I'll do an example next to show you exactly what this looks like in practice. But there's m terms over here. Whatever this power is, you'll have that many terms in the setup. Since we restrict ourselves to working with real numbers, it's possible that your denominator contains an irreducible quadratic factor. This is an x here. So ax squared plus bx plus c, irreducible, meaning doesn't factor. If the denominator of the function you're trying to decompose has an irreducible quadratic factor, we have to ask what sort of proper rational functions could have been involved. And the answer there is, could be anything looking like this. And then the absolute nightmare case is an irreducible quadratic factor that is repeated. And this will contribute a bunch of terms, each one looking like this. Kind of analogous, right? If you have a repeated linear factor, then you'll have a bunch of terms, each kind of looking like the original simple linear factor. If you have a repeated irreducible quadratic factor, then you're going to have a bunch of terms, each looking like the term you would get from a single irreducible quadratic, and you have to build up to that power. So this last case is really unpleasant. You want to stay out of that if you can, but sometimes it happens. So this is your PFD Bible. I know that it looks a little bit complicated. As we work through examples, it'll make a little bit more sense. For now, I'd just like you to get this into your notes so that you can refer back to it to remind yourself. All right. So let's look at a PFD setup. I'm not going to solve the problem. I'm just going to set it up. Let's write the PFD setup for 1 over, let's do x minus 3 times x plus 5 cubed times x squared plus 1. This is a simple linear factor. This is a repeated linear factor. And this is an irreducible quadratic factor. The simple linear factor will contribute just one term, a over x minus 3. The repeated linear factor, because the power here is 3, will contribute 3 terms to the setup. I would write that as b over x plus 5 plus c over x plus 5 quantity squared plus d over x plus 5 quantity cubed. And then the irreducible quadratic will contribute 1 term, but it will have a linear numerator because I have to allow for all possible proper rational functions that could contribute that factor to the denominator. So that would look like ex plus f over x squared plus 1. That is the PFD setup for this function. The x minus 3 factor contributed this term. The x plus 5 cubed factor contributed all three of these. And the x squared plus 1 factor contributed this. Notice that the degree of the denominator here is 1 plus 3 plus 2 is 6. And you would have to find 6 constants. You would have to solve a 6 by 6 linear system to fully perform this partial fraction decomposition. I'm not going to do that. That would take the rest of the class. And I won't give you a problem like this, where you have to find all the constants and then integrate. But if you wanted to integrate this, you would first set it up like this, then run through that exact same procedure I just showed you, then solve the corresponding 6 by 6 linear system, and then you would have to integrate each of these on their own. Notice that none of these are hard to integrate on their own. Natural log, power rule. This one I would split up as ex over x squared plus 1. That's going to be another natural log. It'll require u sub. And then f over x squared plus 1. That's going to be an inverse tangent. So none of this stuff is hard to integrate. It's all relatively easy. And that's how you integrate wonky shit like this.
I have a question. What would you do for something like this if the numerator was like x squared?
The setup would be the same. That would affect you only when you go to build your linear system. So I refer you back to this, right? What we have on the left-hand side here is our original numerator. So after you clear the denominators, the left-hand side of this equation is whatever your numerator is. And so instead of having 1x plus 0 equals this, I would have whatever your numerator is equals that. And that will tell you what your linear system's left-hand side will look like.
Okay.
So for our next example, let's do something out of the textbook, and let's do something like that where the numerator isn't just 1, so you can see how that affects the result. I don't want to do a big sloppy example with something like that. No. This is just setting it up. Something good. Where's something good? Oh. This was one. No. Tell you what, I think I have an example that I like buried as a part of one of these somewhere in here. Yeah, this is good. Let's do this. We're going to take this problem from this step. So we're going to integrate 4x over x minus 1 squared times x plus 1. So a full-blooded example, integral in all, 4x over x minus 1 squared times x plus 1 dx. Here I'm trying to integrate a proper rational function. The degree of the bottom is 3, so I expect to solve a 3 by 3 linear system. I begin with my PFD setup. So I let my reader know that I'm running partial fractions, and then I set it up. 4x over x minus 1 squared times x plus 1. This is a repeated linear factor, so he's going to contribute 2 terms. This is a simple linear factor, so he's going to contribute just 1 term. So my setup looks like a over x minus 1 plus b over x minus 1 quantity squared plus c over x plus 1. Everybody comfy with this PFD setup? This guy gives me these 2 terms, and the x plus 1 gives me just that 3rd term. Now I'm going to cross multiply by this denominator to get rid of all the denominators. My left-hand side will just be 4x, just that numerator left. My right-hand side, when I multiply this term by x minus 1 squared times x plus 1, one of the x minus 1's cancel, one of them doesn't, and the x plus 1 doesn't cancel, so he stays. Plus, when I multiply this term by x minus 1 squared times x plus 1, both of the x minus 1's cancel, and just the x plus 1 remains. When I multiply this guy by x minus 1 squared times x plus 1, the x plus 1 cancels, and you just get, c times x minus 1 squared. From here, I need to multiply everything out, and then I'll collect my like terms. So first I'll clean up the polynomial pieces here that are nice. This is a times x squared minus x plus x. It goes away and we just get minus 1. So that's, I'm sorry, this looks like a plus, it's just a minus. Plus b times x plus 1, I'll leave him alone, plus c times x squared minus 2x plus 1. And now we'll distribute. So I'll have ax squared minus a plus bx plus b plus cx squared minus 2cx plus c. Now I'll collect my like terms. So I've got an x squared here and an x squared here. So this is a plus c times x squared. I'll look for my x's. I've got a plus bx and a minus 2cx. So that's plus b minus 2cx. And then what about constant terms? I've got minus a plus b plus c. So minus a plus b plus c. Those are my constants. And the left-hand side is 0x squared plus 4x plus 0. Right? That's how I can understand 4x as a quadratic. Everybody see why this is the same as this? It might feel silly to write that, but the reason we do it is so that we can equate coefficients. The coefficient of x squared on the left is 0. The coefficient of x squared on the right is a plus c. So a plus c has to be 0. The coefficient of x on the left is 4. the coefficient of x on the right, is b minus 2c. So b minus 2c has to be equal to 4. And the constant term on the left is 0. The constant term on the right is negative a plus b plus c. So negative a plus b plus c has to be equal to 0. And that's your 3 by 3 linear system. Questions on how we arrive at this linear system?
So farther up, when you multiplied everything by the denominators, how come b doesn't also have an x minus 1?
Because b had x minus 1 squared downstairs. So when I multiply b over x minus 1 squared times x minus 1 squared times x plus 1, the x minus 1 squareds cancel entirely.
Oh, okay, I see.
Other questions on how we arrive at this linear system?
How does it just stay as 4x on the left side?
So I'm cross multiplying by this denominator, right?
Mm-hmm.
So when I multiply over here by x minus 1 squared times x plus 1, everything from the bottom cancels. And what's left is just 4x.
Okay.
Does that make sense?
Yeah.
Okay, cool. So when you get to this line, where you cross multiply by the denominator, your left-hand side, what's left here will always be whatever your original numerator was. That'll always be the case, because you're always multiplying by the denominator. So the denominator will cancel entirely, and you'll just be left with your numerator. Any other questions at how we arrive here? Okay, so my next move would be to rewrite this in standard form. That's a plus 0b plus c equals 0. 0a plus b minus 2c equals 4. And negative a plus b plus c equals 0. And then we can solve this system however we want. I strongly recommend elimination. So if I add row 1 to row 3, the a's will go away. So my first move here would be to say my new row 3 is my old row 3 plus my old row 1. And I'm just changing row 3. These are row operations. So rows 1 and 2 stay the same. And when I add this to this, I get 0a. When I add this to this, I just have b. And when I add this to this, I have 2c. And that is equal to 0, because 0 plus 0 is 0. So again, this plus this is 0a. This plus this is b. This plus this is 2c. And this plus this is 0. I just added rows 1 and 3 to get my new row 3. Now if I do the same thing, but I add row 2 to row 3, So my new row 3, capital R for new row 3 is my old row 3 plus my old row 2. Rows 1 and 2 are not changing.
I'm so confused right now.
So we're solving the system by elimination. So in this step, I added row 1 to row 3. So the row I'm modifying is row 3. When I add row 1 to row 3, I have A plus negative A. That's 0A. 0B plus B is B. And C plus C is 2C. I did this to eliminate the variable A in equation 3. Now I'm adding row 2 to row 3, and I'm doing that. Now I'm adding row 2 to row 3, and I'm doing that to eliminate the variable C there. So if I add this row to this row, I'll have 2B. So first 0A plus 0A is 0A. B plus B is 2B. Negative 2C plus positive 2C is 0C. And 4 plus 0 is 4. So you may want to refresh yourself on how to solve linear systems. If you have a method you prefer more than this, you're welcome to use it. But this is how you solve a linear system using row operations by elimination. You should have learned this in pre-calc. It's called Gauss-Jordan elimination. You can also write these as matrices. It's the same sort of thing to use row operations to solve a system with matrices. You could try to use substitution here, but it's going to take a long time. We're done now, because if you look at this bottom equation, this really just says 2b equals 4, right? You've got 0a and 0c. So equation 3 now says 2b equals 4. Which means b is 2. And if you back substitute that into equation 2, we find, what does this say? This says b minus 2c equals 4. So that's 2 minus 2c equals 4. Subtract 2 from both sides, and you get negative 2c equals 4 minus 2, which is 2. So c is negative 1. Now we have both b and c, and I can use those to find a. Really, I just need c. Since c is negative 1, this is the same as saying a minus 1 equals 0. So a is positive 1. So you may want to review solving linear systems if this doesn't seem familiar. If you have another method that you remember and you prefer, again, you're welcome to use it. But we got to have some tool to solve linear systems. And this is the standard tool. It's called Gauss-Jordan elimination, or just row elimination. At the end of the day, what we get is the values of A, B, and C. So here's where we are. A is 1. A is 1, B is 2, and C is -1. So I'm going to come back up here and say, okay, 4x over x minus 1 squared times x plus 1 is equal to 1 over x minus 1 plus 2 over x minus 1 squared plus -1 over x plus 1. Therefore, the integral of 4x over x minus 1 squared times x plus 1 is equal to the integral of each of these. This is 1 over x minus 1 dx plus 2 times the integral of 1 over x minus 1 squared dx minus the integral of 1 over x plus 1 dx. And each of these integrals is easy. They each require a little u sub. This guy, I'll let u be x minus 1. du is dx. This guy, I'll let w be x minus 1. dw is dx. And this guy, I'll let z be x plus 1. dz is dx. And I'll get integral 1 over u du plus 2 times the integral of 1 over w squared dw minus the integral of 1 over z dz. The outer two are natural logs. The inner guy is a power rule. So this is the natural log of u plus 2 times, when I integrate w to the -2, I'll get negative w to the -1, or -1 over w, minus the natural log of z, and I'll slap on my plus c here. And then the final thing is to go back to the original variable. So this is the natural log of the absolute value of x minus 1 minus 2 times 1 over x minus 1 minus the natural log of the absolute value of x plus 1 plus a constant. And that's the game. So by far the hardest part here is solving the linear system. I think that's probably clear. I heard a comment or two there that sounded a little flustered, and that's understandable. A lot of people have different notations and techniques for solving linear systems. So if this part scared you, don't be frightened. Just go back into your pre-calc or wherever you first learned how to solve linear systems and remind yourself how to solve a system of equations like this. Whatever method you're most comfortable with, I'm fine with you using. If you never learned a good method for solving these, then I recommend doing it this way. As far as I know, this is the fastest, most standard, and most consistently reliable way to solve systems of equations like these. Once you have the values of a, b, and c, the integral is more or less trivial. Each one of these is an easy integral that everybody could have done in the first week of class. The worst case scenario is that you end up with some irreducible quadratic factors downstairs. And we haven't done an example like that yet today, besides setting it up in that one problem. So on Monday, I'm going to show you a few examples involving irreducible quadratic factors. Those will end up giving you like inverse tangent integrals. and they're still not bad. The integrals that are output are still relatively easy. The other thing I'll show you, and you're gonna like this, is a trick to avoid all this shit. From this line, if you are sufficiently clever, you can get 2 of the coefficients out for free. Remember, this is supposed to be an identity, true for every number x. So you're free to plug in whatever numbers you want for x here, and the result should be a true statement. That's called the Heaviside, or sometimes called the cover-up method. And I'm going to post something to your modules here, a link to an MIT OpenCourseware lecture where he discusses the Heaviside cover-up trick. So on Monday, I will show you that trick myself if you don't have time or choose not to read it over the weekend. And then I'll also show you a handful of examples involving irreducible quadratic factors in the denominator. But that is all I have for you guys today. I am going to publish the study guide a little bit later today, and I encourage you to get started on that as soon as you can. The sooner you finish the study guide, the sooner you can submit it to me, and that way I can give you some written feedback on your work, and that way you're not surprised by my expectations when the exam rolls around. Remember that for whatever bizarre, mind-numbing reasons, Santa Fe College is closed on October 2nd for UF's homecoming, even though UF is not closed. So our exam has been moved from the 2nd of October to the following Monday, the 5th of October. And you'll have until the 5th to complete the study guide and homework 5. But again, I encourage you to finish both of those as soon as you can so that you can send me questions, send me written work, and we can have a little bit of a dialogue about your work before the test. That's always a good thing. All right, this is where we have to end today. We are out of time, so I hope you guys have a lovely rest of your day. And I will see everybody either in office hours this afternoon or next Monday. Take care, guys.